So we have talked about what is a handle. We defined a handle, and it was really just a concept where we said that while we are parsing a string, any point where we need to make a reduction in our shift reduce parser is a handle. And we don't really know how to recognize these handles, but we know that if it is a handle, then we should reduce. So the question is, how do we recognize handles? And without answering that question, the whole concept of a handle is meaningless. So the first result here is that it is not possible to recognize handles, all the handles, for an arbitrary grammar. So it's not possible to definitively say that I should reduce or I should not reduce definitively for any arbitrary grammar. Okay. So any algorithm that's going to try to do this is going to be a best effort algorithm. It is just going to try to figure out whether something is a handle or not. If it succeeds, great. In other words, if it's able to uniquely say whether something is a handle or not wherever there was a choice, then that's great. We'll be able to build a predictive LR parser. However, if the algorithm is not able to say that, then we are not able to kind of predictively parse using LR parsing in that case. All right. So recall that a predictive parser needs to be efficient. It needs to be linear time. So it can't be a backtracking based strategy to recognize handles. So we're really interested in figuring out strategies to recognize handles efficiently. Now, the strategy that algorithms would typically use is to try and rule out things that are definitely not handles, right? So maybe there's a class of grammars for which we can say that, okay, this cannot be a handle. And if we can say that, then whenever we have a choice, we can consult this database of non-handles and see, is this a non-handle? If it's a non-handle, then we can say, okay, then we need to just shift, all right, or reduce, depending on what is a non-handle and what is a handle. So that's the idea. We're just going to try and rule things out. So sometimes we'll be able to say that this is definitely not a handle, and sometimes we'll be able to say we'll not be able to say anything. We don't know whether something is a handle or not. In which case, we have to kind of do whatever we can in the best case scenario. So we're going to see some algorithms and grammars where this strategy may or may not work. All right. Okay. So even better, algorithms try to rule out prefixes that can never result in handles. So recall that in a shift reduce parser, we are always moving the cursor one step at a time, and sometimes we are reducing. And everything that is on the left of the cursor is called the stack. Now, as we are moving the cursor to the left, we are basically building a prefix of potential handles, because at some point we are going to reduce based on what the prefix is. And if we ever try to shift and we are sure that this particular prefix can never result in a handle, which means it can never reduce back to the start symbol, then we know that we shouldn't be shifting. Or alternatively, if by reducing, the string that we get on the stack is a prefix that can never result in a handle, then we know that that string can never result in a valid parse, and so we don't do that, right? So based on this information, whether something could be a prefix of a handle or not, in a best effort way, we could make choices of whether to shift or whether to reduce. So let's look at an example. Let's use our running example of a grammar, the grammar of expressions. E produces t plus e or t, and t produces int star t or int or parenthesized e. And let's consider this input string int star int plus int. Now let's assume that the cursor is placed right after the first int. And the question here is whether I should shift or whether I should reduce. Now, if I reduce, then I'm going to be I'm going to get t in the stack, and my next token is going to be a star. If I shift, then I'm going to get int star on my stack, and my next token is going to be an int. Now I can so depending on what is my look ahead, so let's assume that my look ahead is 1. I can see what will happen to my stack and the one character that I'm looking ahead. In one case, I'm going to get a t star, where t would be inside the stack and star would be just outside the stack, just on the right of the stack, and we know star because of the one look ahead. And in the other case, we are going to get int star both to the left of the stack, right? So the first case where we get a T cursor star is the case of a reduce, and the second case where we get an int star and then a cursor is the case of a shift. Now, from these two potential prefixes, we can figure out which one to do in this case. For example, if we are able to say that, oh, T star can never be a prefix of a valid handle, if for some reason we are able to say that, then we know that this is not a good choice at all and we should go with the shift. All right, so that's basically the idea. All right, so if it reduces int to T, it will be left with a prefix of T star. And how do we know whether T star is a good prefix or not? Maybe we have some mechanism to figure that out. We're going to talk about that very soon. And so if the string begins with T star, in this particular case, it has actually no hope of being reduced to E. All right. So it is actually, if we look at this grammar, we'll be able to see this. Notice that there is no production that begins with a T star. The only option is here with the T star is to either reduce T to an E and then try, but then there is no production that begins with an E star either. So neither T star can be reduced to anything because there is no production that has a prefix of T star. And even if I reduce the singular T to E using this production E produces T, even then E star cannot be reduced to anything because there is no production that produces E star as the first two characters, first two symbols or first two tokens. And so if the string begins with T star, it has no hope of being reduced to E. And we want to kind of capture this intuition for a general grammar. In this grammar, we can see that if something begins with T star, then it has no hope of being reduced all the way back to E. And we're going to give this a name, and we are going to say that T star is not a viable prefix of the grammar. All right. So what do I mean by T star is not a viable prefix of the grammar? As I said, anything that begins with T star cannot be reduced back to E. All right. More formally, what is a viable prefix? For any rightmost derivation, S to something something, where S is a start symbol, if you take any step where there is some string of terminals and non-terminals, X is the rightmost non-terminal, which means omega here is all terminals. And in this rightmost derivation, because X is the rightmost non-terminal, you basically produce beta from X. So you use the production X goes to beta to go from alpha X omega to alpha beta omega, where alpha is some string of terminals and non-terminals, X is a single non-terminal, and omega is some string of terminals. And similarly, beta is some string of terminals and non-terminals. Now, if there is any such right derivation for any string, then alpha beta, recall, is something that we call a handle. But we also call alpha beta and all its prefixes viable prefixes. So there are two differences here between how we define handle and how we are defining viable prefixes. In handles, we were basically interested in the rightmost derivation for a particular string. Here we are not really interested in the derivation of a particular string, we are saying for any possible string. The second important difference is that not only are we interested in the handle, which is alpha beta, but also all its prefixes, and those are also going to be called viable prefixes. So viable prefixes are prefixes of handles seen during the rightmost derivation of any string. And that's why this is a very good pruning out mechanism. So if you want to figure out that if something is possibly a handle for a given string, you just, if it is not a viable prefix, that means it's not a handle for any string. And so if it's not a handle for any string, it's definitely not a handle for this given string, and thus you can reject it. That's how viable prefixes are useful in shift-reduce parsing. Now, I want to emphasize an important subtle point here, which is that only alpha beta is a viable prefix, but alpha beta omega or any kind of prefix of omega is not a viable prefix. So for example, if omega was, let's say, ABC, then alpha beta A is not necessarily a viable prefix. And this can be seen through this example. So let's take this very simple grammar. S produces E dollar, where dollar is the end of input character. E produces a single non-terminal T, and T produces a single terminal int. So actually this grammar, this very simple grammar actually has, defines a language which is only consists of a single string int dollar. So S, and the rightmost derivation is shown here. S produces E dollar, the rightmost non-terminal is E, so that produces T dollar. The rightmost non-terminal is T, and that produces int dollar. And that's the only non-rightmost derivation in this particular grammar. Now, the interesting thing to note here is that if I want to figure out what are the viable prefixes, E dollar is a viable prefix because it actually fits our definition here. When we're going from S to E dollar, so here X is represented by S, alpha is represented by epsilon, and omega is also represented by epsilon, right? And now beta here is E dollar. So because of this, alpha beta is basically E dollar, and so E dollar is a viable prefix. Now let's go one step further, and now let's look at this production from E dollar to T dollar. Now once again, I basically pattern match with this alpha x omega to alpha beta omega, and once again alpha is epsilon, E is X, which is the rightmost non-terminal, and dollar is kind of pattern matching with omega, which is a string of terminals. And this is going to produce T dollar. So beta is kind of pattern matching with T. And alpha once again is just epsilon, isn't it? So once again, by our definition, alpha beta is a viable prefix. And by that reasoning, T is a viable prefix. But notice that T dollar is not a viable prefix of this grammar, because dollar is a part of omega, and we are not really counting that as a part of the viable prefix, because viable prefixes are prefixes of possible handles, and T dollar is not a possible handle in this particular grammar. So I mean, this restriction that you shouldn't be moving past past the last derivation, wherever the cursor is. So one way to think about it is that if you look at any rightmost derivation, if you look at any one step which basically produced beta from omega, there has to be some such x and some such beta. After all, something has to get produced. Then you place a cursor right after beta, and the string before this cursor is basically a viable prefix, and any substring of that string on the left of the cursor is also a viable prefix. Okay, so this is an important point, and by that reasoning, we may be able to infer that alpha x may be a viable prefix as well, and so on. But I mean, but you have to reason about it by saying that, hey, alpha x is a prefix of some potential handle for some possible string, and you will find that it will turn out to be this. And in this particular example, this means that while T is a viable prefix, T dollar is not a viable prefix. Similarly, I can do the same thing in this step, and pattern match X with T and beta with int, and by that reasoning, int is a viable prefix, but int dollar is not a viable prefix. So let's look at this example. The same example grammar that we have been using, the grammar of expressions. E produces T plus C or T. T produces int star T or int or parenthesized T. Now, which of these are viable prefixes? So the first question is T. Is T a viable prefix? Well, can T appear on the left side of a rightmost derivation of E, which is the start symbol? So let's see. Well, indeed, I can produce E produces T plus E, and in which case, here is T, and it is a viable prefix. In fact, there are multiple ways of producing T as a viable prefix. I could also have just produced E produces T, and that would also have produced T as a viable prefix. And so the answer to this question is yes. Okay. Now let's look at another question. Example. Epsilon. Is epsilon a viable prefix? Indeed, epsilon is definitely a viable prefix. In fact, epsilon is a viable prefix of every grammar, because even the start symbol E has an epsilon as its prefix, isn't it? Or even if I just expand it, maybe I expand it to T plus E, even then it begins with an empty string. So empty string is always present in the beginning of any string. So the answer to epsilon is yes. In fact, epsilon is the viable prefix of any grammar. All right. Then let's look at another example. Is int star a viable prefix? All right. So does there exist a rightmost derivation of e where int star appears as a prefix? Let's look at that. So e produces, let's say, so I want to produce int star. So maybe I can just produce t and then I produce int star t. All right. I could have also produced t plus e and then again int star would have appeared on the right, on the left. And so here int star is appearing as a prefix at some step of the rightmost derivation. And indeed int star is a viable prefix also. All right. So the answer is yes. All right. Next question. T star. Is T star a viable prefix of E? Now let's see. I have two options starting from E. Either I could produce T plus E or I could just produce T. If I produce T, then I have no hope of producing T star, right? Because T is going to produce int star T, in which case int star would be the first two tokens, and that doesn't match with T star. Or it's going to just produce int, which does not match with T star either. Or it's going to produce a left parenthesis, which does not match with T star either. So this is not a fruitful path. Now let's look at T plus E. Once again, if I do a rightmost derivation, then I'm going to first derive E. So I'm going to, have some sequence of steps, and maybe I'm going to get T plus something something. And then eventually I'll have to expand T. So far at least we haven't been able to get T star. Right? We got T plus on the left, but we haven't been able to get T star. And now if I try to expand T, I can only get either int star or int or left parentheses. And so even here, I'm not being able to get a T star as the left prefix of some step of the rightmost derivation of E. And so the answer is no. T star is not a viable prefix of this grammar. All right, let's look at another example. Int star T plus T. Okay, is int star T plus T a viable prefix of this grammar? So once again, let's start with E, and we want to produce int star T plus T as a prefix of some step of a rightmost derivation. So maybe I want to start with E produces T plus E, and then I produce T plus T. Recall that this is a rightmost derivation. So my next step would have to be that I derive T, and so maybe it will become T plus int, or maybe I want to do T plus something else. Maybe I want to do T plus int star T or whatever. But the problem here is that I cannot just retain this plus T and then expand. So, doing something like this is not legal, because then it would be a rightmost derivation. Because in this step, in this particular step, I'm deriving the left non-terminal before the right non-terminal, and so that's not a rightmost derivation. And although this looks like it's producing the desired viable prefix, this is not, this won't count, and so we won't consider this. And you'll see that no matter what I do, I won't be able to produce int star T plus T as a prefix of a rightmost derivation. And the basic reason is this T would get reduced, would need to get derived before the left T can be derived into int star T. And so this kind of a thing cannot happen in a rightmost derivation. And so the answer is no. This is not a viable prefix. All right, finally, is E a viable prefix of this grammar? The answer is yes, because the first step itself is just E, and it has E as its own prefix, right? So E is a viable prefix of this grammar. Okay, so we have some idea of what is a viable prefix by looking at just an example. If I look at viable prefixes in relation with shift-reduce parsing, so far I have defined viable prefixes as how it appears in a rightmost derivation. But recall that a shift-reduce parsing sequence of steps is nothing but a rightmost derivation in reverse. So I can even define viable prefixes in relation to shift-reduce parsing as follows. Alpha is a viable prefix if and only if alpha cursor omega is an intermediate state in a valid parse of any string, right? So you take any string, if that string can be reduced all the way back to the start symbol, such that at some point I get alpha cursor omega, then alpha is a viable prefix, right? This is just coming from the definition of a viable prefix. What is the definition of a viable prefix? Anything that can appear on the left of a rightmost derivation, of any step of the rightmost derivation. So if I just reverse that, anything that can appear as the stack of a shift-reduce parsing, successful shift-reduce parse of any string, all right? So that's what a viable prefix is, all right? So this is an important insight, isn't it? Because it basically means that while I'm parsing, so let's say I've been able to define a language of viable prefixes, and I have some machine that's able to tell whether something could be a viable prefix or whether something is a viable prefix or not. And now I'm parsing some string, and I have some choice between a shift and a reduce, let's say. So now I can see, if I shift, do I get a viable prefix? If not, then that option gets ruled out. Similarly, I can check, if I reduce, do I get a viable prefix? If not, then that option gets ruled out. Now it is possible that both shift and reduce produce viable prefixes, in which case I still have a problem. So that's why I say that it's a best effort algorithm. We don't have there's no algorithm that can do this for all possible grammars. But for many grammars, this kind of filtering of what is a viable prefix and what is not helps us resolve shift reduce and reduce conflicts. Okay, so let's look at viable prefixes and handles. So any prefix of a handle must be a viable prefix. So that is just by definition, because a handle is supposed to be something that appears as a derivation during the rightmost derivation. It is a derivation step. And similarly in the reverse path, it's a reduction step. So whenever we reach a handle in a shift reduce parser, we should reduce. And in both cases, it must be true that any prefix of that should be is a viable prefix. That's just by definition, because if I can derive the handle, then I can also derive. Then the prefix of that handle is also something that is appearing in that particular step in a rightmost derivation. So any prefix of a handle must be a viable prefix, just by definition. And hopefully, whenever we face a choice, hopefully only one of the options produce a viable prefix. So the reason we are studying viable prefixes is because hopefully for many grammars, it may be the case that whenever we have a choice between a shift and a reduce, or between one reduce and another reduce, we can check whether which one is a viable prefix, and based on that we can prune our choices. Alright, so for example, let's say at any step in my parsing algorithm, I have alpha, beta, gamma, cursor, and then A, omega. Here alpha, beta, gamma are strings of terminals and non-terminals. A is a single terminal character or token, and omega is also a string of coterminals and non-terminals. Now first option is I can shift. And so if I shift, what do I get? I get alpha, beta, gamma, A on my stack. And now I can ask this machine that is alpha, beta, gamma, A, does it belong to the language of viable prefixes or not? If the answer is no, then we can rule this out, right? And if the answer is yes, then this is a possibility. We have to keep this possibility. Option 2 is, let's say I reduce by this particular reduction, x produces gamma. Now if x produces gamma, then what do I get on the stack? I get alpha, beta, x. But then I also have a look ahead, and let's say the look ahead is 1, in which case I know that the next character is A. And now I can ask the machine, is alpha, beta, x, A a viable prefix? If the answer is no, then we know that this reduction is not going to be fruitful, and it's not going to lead us to a valid parse. Similarly, maybe there's a third option, and that option is yet another reduce, but through a different production. So let's say this reduces y produces beta, gamma. And now in this case, I want to reduce beta, gamma to a single non-terminal y, and so I'm going to get alpha, y on my stack, and A is the look ahead terminal. And so I want to ask the machine, is alpha, y, A a viable prefix? If the answer is no, then this option can be ruled out. Okay. Alright. So different grammars will have different ways of ruling out certain possibilities. So for example, we discussed how if I have a look ahead of 1, then I can consider A and figure out whether and use that as a part of the string, and then ask the question whether something is a viable prefix or not. If I didn't have a look ahead, then I wouldn't have been able to use A in my questions to the machine. So based on what type of disambiguation or what type of information the algorithm is using to figure out whether I'm on the right path or not, there are different algorithms, and then depending on whether a grammar is parsable through that algorithm, we basically categorize the grammars based on which algorithm can parse those grammars. For example, we said an LL1 grammar is parsable through an LL1 algorithm. Similarly, we're going to say an LR1 grammar is something that is parsable by an LR1 algorithm. What is the LR1 algorithm? It's a shift-reduce parsing algorithm that requires only a look ahead of 1. What is an LR0 algorithm? LR0 algorithm is a shift-reduce parsing algorithm that requires no look ahead whatsoever. Right? So even without doing any look ahead, I can conclusively say at every step whether I need to shift or I need to reduce. That would be an LR0 grammar. So if for that grammar, it is true that for any string, I can implement a shift reduce parse without having to do any look ahead and conclusively, predictively say which is whether I need to shift or reduce. That would be an LR0. LR1 would require 1 look ahead, and so on. So let's say this is the universe of all grammars, which is represented by this square, and I'm going to draw Venn diagrams to say what grammars, how are these grammars related to each other. So let's say these are all the grammars. Then the unambiguous grammars are a subset of all grammars, obviously. And we are only interested in parsing unambiguous grammars, because any grammar that is ambiguous will always have a shift-reduce parse conflict or a reduce-reduce conflict, because we don't even know, because there are 2 possible parse trees for the same string. And now when we are parsing, we don't know which paths to take. And so obviously there will be a problem. So when we are talking about these algorithms, we are only looking at unambiguous grammar. So there exists only 1 parse tree, but now are we able to find that parse tree or not? That depends on the capability or the precision of the algorithm. And so we are only interested in unambiguous algorithms. For example, LR1 may be more precise than LR0 and so on. So that's what we want to see. Okay, so of some subset of all the unambiguous grammars are the LR1 grammars. So these are the grammars that are parsable through the LR1 algorithm. So the bigger the set of grammars for a given algorithm, the more powerful that algorithm is. That means it can handle more grammars. A subset of that is LALRs. LALR is a simplification over LR1. So LALR1 is also 1 look ahead, but it's simplification of LR1. We haven't discussed it yet, but we're going to discuss it in the subsequent modules. Further, the LR0 grammar is actually a subset of both LR1 and LALR1. So the green oval here represents the set LR0, and this is expected. Anything that you can parse at LR1, LR0 you can always parse at LR1, because we just have 1 extra look ahead. But the interesting thing is LR0 is also a subset of LALR1. And there is yet another algorithm called simple LR or SLR, all right? And simple LR is weaker than LALR, but strictly stronger than LR0. Okay, most grammars in practice are LALR1, and that is what is actually implemented in tools like Bison by default. Now, you may ask at this point, how does LL1 fare with respect to these grammars? So, is it true that LL1 is strictly less powerful than LR1? Is it true that LL1 is strictly more powerful than LALR1, or whatever? What is it, right? So once again, what am I asking? I'm asking whether there exists a grammar that is parsable using LL1, but is not parsable using LR1. All right. So these kind of questions we want to answer, and that's very nicely representable using this Venn diagram. So this purple line here represents the set of LL1 grammars. Of course, this is not to scale, but basically what it means to indicate is that LL1 is a subset of LR1. So any grammar that is parsable using LL1 is also parsable using LR1, and that's why we say that LR is more general than LL. Okay. However, it's not true that LL1 is more restrictive than LALR necessarily. There exist some grammars that are parsable using LL1 but are not parsable using LALR1, and similarly the other ones. Similarly, there are some grammars that are parsable using LA LR1 and not parsable using LL1. All right, so that's what this Venn diagram indicates.